So this is our last official lecture of the entire semester. And in this, we will go over probably the most common types of polymers that exist in consumer products, in things that you would buy at a store, things that you would encounter in close to everyday life or everyday life, depending upon your industry, your job, or what kinds of things that you encounter daily. And so we ended on Monday by talking about vinyl polymers. That is the substances that are derived primarily from compounds that have this as their monomer. This is the vinyl compound, where I've got two carbons that are double bonded to each other, hydrogens around it, and then some sort of subgroup here. And that subgroup is just something that we don't know what it is. And depending upon what that subgroup is, it could be as simple as a hydrogen or maybe another carbon-based group, a hydroxyl group, a chlorine or a bromine or an iodine or sulfur. There are lots of possibilities in that area. But depending upon what's in that, we're going to have different kinds of compounds, and they're going to make different kinds of polymers that have slightly different properties. We started our discussion on Monday with polyethylene. Polyethylene has as its derivative the simplest of these vinyl compounds, and that's with the hydrogen in that spot. Now, polyethylene comes in two different forms. There is the high density polyethylene. We know that as either HDPE or number 2 plastic. There is also low density polyethylene, LDPE, and that's number 4 plastic. These substances tend to be relatively rigid because they are thermosetting polymers. There's not usually a whole lot of give to them, but they make very good containers. So this bottle of sanitizer, yeah, this is number 2. This is high density polyethylene. Again, remember, thermosetting, once we mold them and once it cools, it holds its shape. So we get some rigidity here. And so products like these kinds of rigid bottles or toys, those reusable plastic bottles that you find at the store, those are often high density polyethylene as well. Products like toys are often number 2 or usually number 4 plastic, especially if you want them to have any kind of give at all. The lower density does tend to have a little bit more of a softness to it. It's not as hard and rigid. Both are capable of being recycled. The big key attribute of them is their density is considerable. Their fuel density is considerable. That means lots of heat when they burn. And by mass, these will burn hotter than any other polymer. So gram per gram, we get more energy out of them than anything else. Polypropylene, number 5 plastic, is another very common one. The starting material for this one is where we have the other CH3 group hanging off of the end. Polypropylene is very versatile. We can see it used in a variety of products, some of which will give us kind of the silky fibers. Some of them will give us rigid containers. In its fibrous kind of application, we see polypropylene used for things like shatterproof glass in hockey arenas, artificial turf on football fields and in soccer stadiums. It can be used in making twine or rope or carpeting. In its container applications, polypropylene is often used for those small, flexible kinds of bowl-like containers. And you know the ones I'm talking about. They usually hold things like sour cream or cottage cheese or yogurt. They're usually a thin plastic that's kind of flexible when it's empty, but holds its shape pretty well if it has something else in it. Most places, polypropylene is recyclable. And what's interesting about it is it's not terribly flammable. What we will see more often with polypropylene is it will decompose. And so we'll either see a melting kind of composition with it, where it kind of melts a little bit, drips. And as it does, it'll start to decompose and form vapors, and the vapors themselves can catch on fire. If I take a piece of polypropylene and put it into a flame, I'm not going to be able to pull it out and see the whole thing on fire. It doesn't really do that. Polyvinyl chloride, also known as PVC. PVC is derived from the vinyl chloride. Vinyl chloride, as you might imagine, is the vinyl compound with the chlorine in that spot. On its own, vinyl chloride is pretty nasty and dangerous stuff. Vinyl chloride is flammable, and it is a prime target for autopolymerization. Remember from our previous lecture, autopolymerization is the phenomenon where a compound can just spontaneously form a polymer just by sitting around. The conditions are right to get the reaction started without an initiator, and we just end up getting a gummy mess instead of the polymer that we see. Vinyl chloride is widely recognized as a carcinogenic material, meaning that vinyl chloride will cause cancer if you are exposed to enough of it for a long enough period of time. However, when we get it to polymerize properly, it makes a pretty good building material. PVC piping is one of those materials that has become very, very popular for its relative price, the rigidity of the plastic itself, and the fact that it's not going to corrode over time, unlike metallic piping. Even the best metallic pipes out there will eventually break down and decay and corrode because, well, there's oxygen, there's water. That's usually a good recipe for rust if we're talking about something iron-based. And there's other stuff in the water that can slowly degrade it over time as well. PVC solves a lot of those problems. It's also, generally speaking, recyclable. Now, its recyclable nature largely depends upon where you live and what kind of recycling restrictions are available. Here in Vincennes, PVC is not something that you'll be able to recycle just by leaving it in the recycling can next to your house on recycling day. However, there are certain times of the year where recycling can be done for those kinds of materials. You just have to kind of watch out and check your local news, and they usually tell you when those are going to be. But it is a recyclable material. The problem that you run into with a lot of recyclable materials is certain types of materials are easily contaminated. And if they get contaminated too much, their value as a recyclable material decreases considerably. And that's why some places just don't take them anymore. Here in town, we used to take plastics 1, 2, 3, 4, and 5. We used to take all of them. Over time, whether it was through abuse of the system or otherwise, they've pared us down. We only take 1, 2, and 5. 3 and 4 are no longer taken here in Vincennes. Some other places do, we don't. The same problem you run into in a lot of cases with glass. Glass is really hard to recycle in some cases. Because the glass has to have a certain quality to it in order for it to be properly melted down and redistributed. And a lot of glass just doesn't meet that criteria. So the business that takes it often doesn't want to take it. It just says, no, we're not going to take it anymore. Problem with PVC is that when it burns, that chlorine attachment on the molecule pops off. And when it combines with water, vapor, or any other product from the fire, we end up getting hydrogen chloride gas. Hydrogen chloride gas, well, combine that stuff with water and you've got hydrochloric acid, which is a pretty nasty corrosive. Another big issue with PVC is that those chlorine compounds can end up forming something called a dioxin. Dioxins, generally speaking, are chlorine derivatives with oxygen along this variety, ClO2. Now, there's usually more that goes into it. That's why we don't give it a specific formula. It's kind of a class of compounds. But the idea here is relatively simple. Dioxins are highly reactive chlorine compounds. And if you breathe in dioxins, which would be a really common circumstance, that high reactivity ends up making its way into your respiratory system, your circulatory system, and can cause you a lot of pain and potentially disease and illness depending upon exposure and duration and all those other things that we talked about in the toxins chapter. So pretty nasty stuff when it is formed. It can cause death in the appropriate concentrations. It's nasty. Acrylonitriles. Again, starting with our vinyl compound, the acrylonitrile has a CN group in that extra location. Acrylonitrile on its own is volatile, toxic, and flammable as a liquid. as is the case for a lot of these monomers that we talk about, on their own, they're relatively reactive and they're kind of nasty to get around. They're either corrosive, flammable, toxic, or some combination of those things. But where we see acrylonitrile being used most often is in the formation of acrylic fibers. Acrylic fibers, by definition, are fibers that are composed of at least 85% by mass of acrylonitrile. Now, acrylic fibers have a lot of uses. We can see them woven into textiles. Certain types of fabrics like Orlon, Acrylan, both of those are owned by the DuPont company. Those are in carpets primarily. So if you have something like a stain resistant carpet or a carpet pad that does not absorb liquids, doesn't absorb stain, it is the acrylonitrile fibers that are the main cause of that. You see the same kind of thing for certain types of fabrics, not your moisture wicking fabrics, but fabrics like these dress clothes that would be resistant to absorbing water. So in the event that you spill something on yourself, the acrylonitrile fibers actually wick away a good bit of that so that it doesn't get absorbed, it doesn't ruin your pants or your shirt or whatever it is that you're talking about. We also see these used in nitrile gloves, which have become very, very popular in the last 17 months. Those have polyacrylonitrile at their base. We also see it woven into other types of fabrics. Many of your traditional sweater materials. And I'm not talking about sweaters like the stuff that's made out of cotton polo material or sweatshirts. I'm talking about kind of your traditional Christmas sweater kind of look. The ones with the woven fabrics that are kind of woolly. Well, the ones that aren't actually made out of wool are often made with a blend of cotton and acrylic fibers. And if you look at the composition on those, you'll usually see made from 50% acrylic fibers, made from 75% acrylic fibers. So these are usually pretty versatile materials. Now, the natural hazard associated with them is you might recognize this group, CN, and say, isn't that cyanide? Well, not quite. Cyanide would be CN -1 charge. It'd be an ion. This is not cyanide when it is bonded to this molecule. However, when this molecule burns and it starts to disintegrate, that CN group suddenly becomes available. If it attaches to a hydrogen, then we have hydrogen cyanide gas, which, yes, we did talk about that in our toxins unit. And yes, it is really dangerous. Let's move on now to polymethylmethacrylate. This is actually a class of polymers, so I'm not going to draw the monomer structure because there really isn't one single structure. But what we have here are polyvinyl polymers that are produced from esters of acrylic acid and methacrylic acid. So It's polyvinyl, but it's got some elements of condensation polymerization in it as well. These substances on their own prior to polymerization are volatile and flammable, but they make some pretty cool compounds. Plexiglass being one of them. So that's your kind of artificial shatterproof glass. You can find it in a lot of places. Again, plexiglass has been a common variant used for making barriers. Again, in this more modern day and age, in the post-COVID world, it's been used to make barriers so that people can sit near each other but not actually be near each other. So plexiglass has been used for that. Lucite is another variant. It is a clear kind of plastic material. And it also is derived from this class of polymethacrylate compound. We're starting to get now into some compounds that are condensation polymers instead of vinyl polymers. Polyurethane is one of them. Here we get a substance produced by the condensation of glycol and organic diisocyanate. Now, these two substances on their own, glycol, diisocyanate, they're liquids. Nothing really too spectacular about either one of them. But what happens when you mix them is that they'll actually start to foam up. And so you start to mix them up, they start to get kind of frothy. And then all of a sudden, that froth goes from just kind of your normal foamy kind of, I don't know, almost fizzy shaving cream-like material to rock hard solid. The resulting foam is polyurethane. The polyurethane foams have a lot of different applications. They have a certain amount of density, despite the fact that on their own, they're not terribly heavy. They look big and impressive, but they are just a foam nonetheless. They just happen to be kind of a dense foam. So where do we see them used often? Soundproofing, insulation. You make a studio and you want to soundproof it so that you don't drive the rest of the people in your house crazy while you're banging on the drum all day. Polyurethane foams can go on the walls, the ceiling, in the insulation. And they will deaden the sound. They will help to contain the sound to that one room. We also see polyurethane. Yeah. So remember, there are two types of polymers primarily. There are the addition polymers where we just take those double bonded vinyl chlorides or whatever, and we just link them together one after the other. And then there are condensation polymers. Condensation polymers are where we take two different compounds and they will basically alternate with each other. And while they do, they will drop small amounts of another product along the way. That's the condensation part of it. So in the case of this one, with glycol and diisocyanate, we're either going to see water or maybe something like hydrogen cyanide or um, uh, cyanic acid or something like that. Yeah, so it's the train picture where every other car is different. And when those train cars connect with each other, they drop a small molecule along the way, a water molecule, a small acid, a small base, something along those lines. That's what we mean by a condensation reaction. The reaction occurs, but it has a byproduct that occurs as the chain is forming. Whereas addition polymers don't have a byproduct. We just link up one after another, after another, after another. So with polyurethane, we can also see it used for flexible foams. This can be made into things like mattress pads, the padding that goes underneath carpet to help it feel soft to the touch on your feet, cushions in your furniture. So usually your couch cushions are made out of polyurethane foam. The seat in your car is usually made out of polyurethane foam to give it some cushion. Now, this is different from memory foam. Memory foam is a different polymer. That's why memory foam has certain kinds of properties to it in terms of springiness and other things that we don't see as much with polyurethane. Polyurethane foams tend to be a little bit more rigid because they're usually supporting more weight, and they're usually used just to kind of provide some kind of a barrier. So if you put a mattress pad on your bed, not a memory foam, but a mattress pad, the whole idea is to give you a little bit of extra space between you and your mattress, which might be a little bit too hard, and your box spring, which is definitely hard. And that little bit of extra barrier makes the bed feel softer while still maintaining some of the structure and sturdiness of the mattress itself. All right, let's move on to some other kinds of polymers, ones that have specific kinds of uses. So here we've got Teflon. Teflon is polytetrafluoroethylene. So we're back to a vinyl polymer, kinda. Instead of having hydrogens all over the place, what we end up having here are fluorines all over the place. Teflon has a lot of different kinds of uses. On its own, it's pretty tough to break Teflon. If I have a solid material of Teflon, it's pretty hard to destroy it. So it makes good applications for certain types of tubing or gaskets or valves. Upside with it is that they're not going to break down. Downside, it's a lot more expensive than rubber, which is what is usually used for tubing gaskets and, well, not so much for valves, but is quite heat resistant. And it is quite corrosive resistant. So I can put acid on top of Teflon, really doesn't phase it. I can heat Teflon like crazy, really doesn't phase it. Teflon is used in a number of different applications along these lines. For plumbing, for example, there is a particular Teflon product that looks like a little roll of tape, and you put it around your water seals, at your washer and dryer, well, not your dryer, but at your washer, your your water heater, other places to help create a nice tight seal so that water doesn't leak out. And the Teflon tape generally keeps it in, keeps it from coming out, and does a pretty good job with that. Teflon also had a particular craze in the production of non-stick cookware. If you got good non-stick cookware, especially in the 1990s, it was usually Teflon coated in some kind of way. And if you got good Teflon cookware, it usually lasted a pretty long time, unless you use the wrong kind of material on it and start scratching the Teflon off, and then it becomes pretty useless. Because once the Teflon starts to chip off, it all starts to chip off. And you don't want to end up eating Teflon as a result of that. Nowadays, there is still Teflon cookware out there, but a lot more of the non-stick materials have switched to ceramic based kinds of things as opposed to Teflon. Nomex. Nomex is a polymer that is primarily used in the making of fire suits. We also see Nomex used in a number of varieties for things like anybody watches NASCAR, Formula One, IndyCar, those special racing suits that those guys wear. One of the reasons why they burn a tremendous amount of calories during the course of the race, because they're sweating their tails off of these things. But it's got a derivative of Nomex in it so that if something went bad, the likelihood that they would catch on fire as their car is catching on fire is considerably lower. And the way it works is upon intense heat, the Nomex actually will transform and carbonize and thicken and provide an insulating barrier between the person and the fire, which protects them from the fire. Kevlar. Kevlar is a flame-proof material, but we probably know Kevlar most and best because when we draw Kevlar into fibers and then take those fibers and weave it into a textile of fabric of some sort, that resulting fabric has a greater strength than steel. And not just by a little bit, by fivefold. So imagine in the Middle Ages, the guys wearing the chainmail everywhere. Now, heavy that stuff is. The whole point of the chainmail was to prevent you from getting seriously injured by being impaled by a sword, which wasn't always terribly effective at that, but trade that for today with Kevlar, you got a considerably lighter material that is actually 5 times stronger than that of chainmail or of steel or anything along those lines. So with Kevlar, we can talk about things like bulletproof vests. We can talk about things like certain types of compression material that is going to be protective as well. We can talk about rubber. With rubber, we have 2 primary properties that we want to preserve. And that is, we want rubber to be flexible. So rather than breaking apart or cracking when we put stress on it, we want to see rubber actually deform. That is, if I'm driving down the road and I hit a bump in the road, I don't want the tire to pop because it's so rigid that it doesn't move. I want to see that tire compress slightly so that it goes over the bump, and then once it's out of the bump, just goes back to the way it was. And so what we see there is the flexibility of being able to deform when it is stressed, but also the recovery strength to pop back to the original position once it has been stressed. Now, where we can get that elastic recovery comes through a process known as vulcanization. Vulcanization is a process where we heat natural rubber and add to it elemental sulfur. Elemental sulfur, as we talked about at the beginning of this unit, ends up acting as a cross-linking agent, which will take those rubber polymers, which were kind of sticky and not terribly cohesive, and lock them up and strengthen them. With vulcanization, you can then take the resulting rubber that has been strengthened and cast it into a number of different shapes, and those shapes will actually hold their shape once the whole thing sets. And so here are some of the different kinds of products that are made using rubber or rubber additives. So things like shoes, in particular the soles of your shoes. Most of them are made from rubber or rubber derivatives. Now, not all of them are made from natural rubber, but there are a good number of synthetic rubbers out there that do just as well, and often a little and good bit cheaper. We also see it used for things like rain jackets, rubber tubing and rubber hoses, tires, rolling materials, whether it's rollers for producing textiles or other kinds of fabrics. We see rubber used in a lot of types of machining and processing, especially for things that are relatively soft or pliable, that we want to come out very flat. Now, those are all different applications, and they all have different kinds of purposes. There's a vulcanization process for each one of them. The more sulfur that we add, the more rigid the structure will end up being. So sulfur content in your rubber is going to play a big part in how flexible, how soft that rubber is going to end up being. The more sulfur we add, the more rigid and shape holding it's going to end up taking. As I mentioned before, not all of the rubber that exists out there in the world is actually derived from the tree sap natural rubber sources. In fact, about 65% of the rubber that exists out in the world today is actually synthesized. And so it's not actually true rubber. What it is something that is called an elastomer, basically a polymer that has been created specifically that has elastic-like properties. Meaning we can stretch it, but when we're done stretching it, it snaps back to its original state. And so only about 35% of the rubber that is created actually comes from natural rubber sources. The rest is made in a laboratory somewhere. There are a couple of common ones that are out there. SBR, styrene butadiene rubber. This is the primary rubber derivative that is used to make tires and tire treads in particular. Neoprene rubber, we see these used especially in the oil and gas industry. These are ones that are particularly resistant to petroleum products, ozone products. So we see these in a lot of things like mechanics gloves. Now, other places where you would have considerable opportunity to work with and touch other kinds of petroleum products, oils, gases, diesel fuel, and so on. And they're chemically resistant, which is a good thing because otherwise, a lot of organic solvents will actually start to eat away at certain types of rubber over time. And so if that's what you work with, you don't want to be hanging on to those for too long because then they'll start to eat away at your gloves and you'll have a mess on your hands. The big issue that we run into with rubber is that when it burns, all that sulfur gets released. And when sulfur burns, we get sulfur dioxide. We talked about sulfur dioxide in our toxins unit. It's that's pretty gross. But I mean, it's nasty if you inhale a lot of it. But the real thing that really draws you away is its smell. Sulfur dioxide, burning tires have a terrible smell that can literally just steal your breath away. Oh yeah? Chokes you, doesn't it? Yeah. Sulfur dioxide is not something you want to mess around with. The other thing that you see, you get very, very dense black smoke coming off of rubber fires because, again, you've got so much carbon and hydrogen, so much to burn through, not nearly enough time to burn through all of it. Neoprene, that rubber derivative that we talked about, because it has chlorine in it, will also give off hydrogen chloride gas as it burns. This is a tire fire, literally. This is a fire that was set by accident in a landfill when a lightning strike hit the landfill. And you can see all those tires that are on fire, they give off a massive amount of heat. And just look, all that smoke there, all that thick black crud coming off of them. This was not the normal kind of fire that you had a couple of guys come in a truck and just put out. Because of the density of the smoke, because of the massive amounts of sulfur dioxide that are being produced, usually special kinds of fire extinguishing agents are brought in. Some of them are flown in over helicopter. Some of them are hooked up to the trucks themselves to provide extra protection and trying to combat that fire and contain it much more quickly. And that is the end of our course. So on Monday, we will get into the final exam itself. We'll talk about what's on the final, how to study for the final, and we'll get into a little bit of the practice test itself. And then we'll follow that up on Tuesday at 9 o'clock. I'll tell you what room we'll meet in on Monday. Tuesday at 9 o'clock. If you are available, we will hold an extra review session, an extra prep session to get ready for the final Friday morning. Remember, final on Friday is at 8 a.m. next Friday. So 1 week from today, right here, 8 o'clock. So it's gonna be like a normal class day, only you get 2 hours of fun instead of just one. Have a great weekend. Yeah. Yeah, that was taken by a company in Virginia.